Today I want to discuss the Boltzmann Maxwell speed distribution graph. And the first thing that I want to begin with is a postulate from kinetic molecular theory, which says that gas particles are in constant random linear motion colliding elastically with containers wall. So we all know that the gas particles are in constant motion, but actually gas particles have different speeds, and we'll know that from this formula, that different speeds indicate different kinetic energy. So gas particles in a container have different speeds and hence have different kinetic energy. So we need something to describe or demonstrate the different speeds of a particle in a certain or particular container. So we have our Boltzmann and Maxwell speed distribution graph. So for Boltzmann speed distribution graph, we have on the x-axis, right, we have a certain range of speeds, like let's write here speed, and for the y-axis we have the number of atoms or particles, number of particles for each speed, right? So for this particular speed here, we might have this amount of particle, and for this particular speed we might have this amount of particles, and so on. So this graph demonstrates the speeds of each particle, the speed of each particle in a certain container. So typically in the speed distribution graph, there are very few particles having low speeds and very few particles having high speed. Most of the particles actually have speed in between. So regularly the graph would look something like this, right? Let's draw this again. All right, something probably like this. Let me draw this again. Right. So we notice here that for the highest speed there are few particles, for the lowest speeds there are few particles, and most particles have speed in between. And actually, remember this, so this is very important. The area under the graph represents the total amount of particle in the container. So this is a very important concept that we will use to solve a lot of problems. The area under the graph is the total amount of particle in the container. Right. So let's discuss the effect of changing temperature on the speed distribution graph. So if we increase the temperature, the effect that we will notice on the graph, that the graph actually is getting wider and shorter. But why is this happening? So as you increase the temperature, the speeds of the particles obviously has to increase also. So increasing the temperature leads to the speed of particles to increase also, right? So you will have a greater range a greater range of speeds available to the particles, and the average speed actually has to increase. An important thing to highlight also is that the peak of the graph here, for example, the peak of the graph is where you most likely will find the average speed. It actually probably will be very close to this point, but not necessarily at the peak. However, at the peak, the average speed will be very close to the peak of the graph. So as you increase the temperature, the average kinetic energy will increase, and hence the average speed has to increase also. So here, as you increase the temperature, you notice that the peak is moving to the right, but it also gets shorter. The number of atoms or molecules at the peak is lower, because now you have a greater range of speeds for particles. So more particles will have higher speeds, and more particles will have lower speeds, and less particles will have the average speeds, or be close to the average speed, because now you have obviously a greater range of speeds. So the peak length has to decrease, because the area under graph is the total amount of particles. So as you increase the temperature, if you had this graph, then you will have greater amount of particles for the same container, and this is not true. So to sum it up, for a cold gas, as you increase the temperature, the graph would look wider and shorter. Would look wider because you'll have a greater range of speed, and would be shorter because you have the same amount of particles as you increase the temperature. After that, let's discuss the effect of having different molar masses. Basically, the effect of having different gases at the same temperature. So for these gases in the graph, oxygen, nitrogen, water vapor, and helium, hydrogen, they're all at the same temperature. For example, at room temperature at 25 degrees Celsius. However, we notice that every gas has different speed distribution graph. So at the same temperature, they all have the same average kinetic energy. But we know that the average kinetic energy can be calculated from this formula, half mv squared. And we notice that the mass is inversely proportional to the square velocity. And we know that the higher the mass, or the lower the mass, the higher the average velocity, right? So even though all of them has the same average kinetic energy, each gas has different speed distribution, because they have different average speed or average velocities, right? So the gas with the lowest molar mass, H2, we notice that it has the graph that is the widest, and it has the shortest peak also. So as the molar mass decreases, we get a shorter graph and wider graph. And that's it for this video.